Okay, so we're going to talk about clustering now. And in the curriculum, the first clustering algorithm, which actually most, I think, um, like learning, like if you were to learn about clustering first, you probably would learn about K-means, because K-means is relatively straightforward to understand and stuff like that. So let's do a little bit of intro. So note that, remember, clustering is going to be unsupervised learning. So unsupervised learning means that we don't have any labels to what we're, what's it called? What we're what groups things belong to. So in supervised learning, we'd have like class A, class B, class C, and so on. In clustering, basically, there isn't a known class. So the idea is that we're going to actually use basically if things are near each other, if those belong to groups. So if you remember this diagram right here, I think I've shown this like maybe a few times now, but basically clustering is saying, for example, ignoring the colors right now, you can imagine like this inner circle and this outer circle are each a group, kind of like this orange and then blue over here. You can see kind of like these moons right here. You can see how there's kind of like more or less groups right here. These oblong kind of like lines going through here, you'd expect those to each be its own group. Obviously, these blobs would each be its own group. And then this last one, I would actually argue that most of this probably aren't. It's just one random noise group. So you can kind of see like how you can group things together. And basically, all clustering algorithms basically start with saying, they don't know what the groups are, like what the groups are. And basically the algorithm's job is to figure it out. Okay. So, so you can kind of think of like what situations clustering would be useful. Anyone have an idea of when you would use clustering in like what application?
Market segmentation is a big one.
Yeah, that's right. Market segmentation is a huge one. Basically, just knowing who your customers are. You can try to define them. Like if you ever hear marketing people talk about things like, oh, women or men of age, 23 to like 34, like shop in this way or react in these ways to these kind of things. Like basically, like what they would have to normally do is kind of segment the population to what would seem like logical clusters, but clustering algorithms actually say, hey, we don't base it on anything other than the fact of whatever we measured. Note that basically then that means that you might have clusters which you might not have ever seen before. Like, wait, I never thought of this as group as like very similar to each other. And that's where clustering really defines or really relies on the fact that things that are close together are similar to each other. Okay, cool. So let's check out what K-means and how to perform this. So I'm just gonna kind of go through these steps, but then I also have a little visual. So just kind of know if this feels like really like I'm still not understanding, we're gonna show you a little visual like how to walk through it. So first, basically you wanna determine how many clusters there are. So K means just like K nearest neighbors. K represents saying how many clusters. And then we're going to initiate random centers. Technically there's other ways you can initiate, but usually random's going to be most common way. And notice that this is very important. This will actually set in motion the rest of the algorithm. And basically what you're going to do is you're going to repeat this process of assigning groups and then optimizing it. So the first step basically in this like repeated over and over and over again is you assign, say okay, here's my cluster, or here's my centroid, my center, and say determine which points in that data set are closest, and say, okay, like you're closest to this data point, that means you're going to be class A, and then say, well, the rest of you, you're close to this data point or center, you're going to be class B. And then what we do, the second step is optimize, where essentially we move the centers to optimize to be as close as possible to the overall group. So if you imagine like if you're off to the side here and this is kind of your group, you want to move closer to the rest of that group. Same thing with like each cluster. And you just keep repeating this over and over again until basically you either have so many iterations where you stop, or basically where no points are really assigned anymore, or there's kind of like a stopping condition. So I think this works best if we actually check out this visualization, which this blog post right here is really great. I think this is great. You can also kind of go through, he talks a little bit about like K-means and stuff like this, some stuff we talked about. Definitely check this out if you have the time. But we're gonna go ahead and randomly choose these points. And we're just gonna go ahead and choose, like these are different data sets we could choose. So we're gonna do the Gaussian mixture. So you can clearly see like there are clearly three groups here. So let's pretend we know that there's supposed to be three groups. We're gonna add 3 centroids. And no, this is supposed to be random. So you can see already is that these two are just randomly just put there. And what we're gonna do now is we're gonna say, okay, you can see this blue right here and this green and this red section. What that's saying is that these points that are in the red section are closest to this center. And this, everything in blue here, those points are closest to blue. And you can see right here, these are closest to green. So we're going to label those. So we're going to go ahead and proceed 1. And you can see we assign the points. So now these points are all blue because basically these points are closest to the blue center. These are all green because it's closest to the green center. And these are all red because they're closer to the red center. Note, however, this red, for the most part, looks pretty good, right? You're like, yeah, that's what red is. But you can see we already got a few extra points because like technically they are closer to red than they are to this blue point. And so what we're going to do now in this next step is optimize. So we're going to move these centers to basically be closest to the points that are already assigned. So what we're going to do here is like, okay, like, well, this blue, it's assigned these points and these points. So what it's going to do is trying to optimize. So it's like what's it, like the smallest, like you can think of like the root mean square. It's like the shortest distance to all of them. So you can imagine this blue point is going to kind of go towards this direction. So basically it's close to these points and these points. This green will probably move closer to the center right here, basically making sure it's kind of more centered with the rest of the points. And this red is probably going to move closer to this center point, but it'll also kind of be pulled a little bit in this upward direction, but not a huge amount because most of the points right here are like, there are more points right here than there are up here. So we're going to update those centroids and you can see you're about right. See, red moved up a little bit, green moved a little bit off the center, and then you see blue basically splitting between the two. So now we moved them over. And then we do the process again. We say, okay, let's reassign the points. So you can see everything that's in blue here are now going to be blue points. Everything that's in green is now going to be green points, and everything in red here. So you note that basically red lost a few of these points. Blue lost a whole lot of these points. It's moving over into this top right, and this green is going to overtake this whole center or section right here. So we reassign the points, and you can see now we're pretty much like where we are. So we're going to update the centroids, and you can see now they're basically centered within each of these groups. So obviously, if I try to reassign the points, you can see nothing's going to change. And then I try to update centroids, nothing really changes essentially because it's already in the center of all these points. Okay, does that make sense to people? Cool. All right. So I love this guy right here because you can kind of play around with a little bit of how you want to do this. There's some extra, let's see here, like there's some extra like different groups right here. So this might be kind of interesting. So we'll talk about this a little bit. But anyway, that's the basic K-means algorithm. Okay. So evaluating this. So one big thing is actually figuring out K. So if I actually go back to this again and I do Gaussian mixture, if I had only like 2, right? Let's say I don't know how, I never looked at this data beforehand. I don't know how many clusters there are. If I put 2 here, you can see that it's not going to do a good job actually finding this third one. And you can see if I go here real quickly, it's kind of assigning it. It's going to basically choose one or the other side, right? So this is going to swallow this side. And that might technically be like, oh, these are more close to each other than this one, but that's not really what we want. We really wanted 3. So if I wanted like 3, that's what I would have. But let's say we had instead like 4. And so this 4 obviously is not going to perform very well in the sense that like, we're not going to get like those 4 different groups. Really, like this group right here probably should be its own group rather than 2 different groups. So figuring out K actually is a really important aspect, right? So how do you determine K? The short answer basically is you just try a bunch of different times with the different Ks and see how good the square distance, basically how much of an error there are between the groups. So obviously if you have very few, it's called very few centers, basically what's going to happen is that your error is going to be relatively large. So like that blue, for example, when we did just blue and red, the blue kind of sat in the middle between 2 groups, and the red's going to be very close to that other one. So you're going to have a very high distance for each center. And what we can do, we can keep increasing K, and as we increase K, the centers are going to find points that are very close to it. But at a certain point, it's not going to drop very much. So you can imagine like if I added like a whole bunch of centroids. And I don't know even how long this was for. Oh, look, this blue got all by itself. But you can see here now, like technically these points are like very close together, right? So your error is going to be relatively small, but it's not going to be that much smaller than if we started off with just 3 of them. Like there's not really that much more improvement for these different groups. So that's essentially what this K elbow plot is going to say. Is as we increase the number of those K centers, essentially, the accuracy is not going to increase or not going to decrease that. Sorry, the error, basically, the distance between the different points is not going to drop that significantly. So we'd get something that's saying, okay, like we're going to stop right here because error's not really dropping that much. Okay, does that make sense? Okay, any questions on either how K-means is implemented or how to find K? Okay, cool. Obviously, note that the big thing right here is figuring out what K is. That's kind of obvious in the sense like we need to know how many clusters we need to do, and the best way to do this essentially is to just try out different Ks, right? Note that you probably wouldn't want to do like one on each one, like 1 through 100, because essentially you have to run the algorithm 100 times, right? So you might do something like you say, okay, let me try it, with 1, 2, 5, 8, 16, and see if you can extrapolate, what this square distance is going to do. And then if you find something, it's like, oh, it looks like it's really bending over here, you might run the algorithm again with maybe some points that are centered on this point. Okay. So this will lead us into some issues. So this is kind of an interesting aspect, is that there are going to be some issues with K-means, and there's some, I think this graph shows a really good example of this, and these are different data sets. So if we remember back to data generation, you can kind of see that, for example, we have our blobs that are classically kind of done here. And this is K-means right on this column. And you can see here also, like we have the make moons, right, data set right here. We also have the concentric circles. So you can see that K-means does not tend to perform very well. There are technically some ways we can get around this. Basically, like think of like the kernel trick, where we can basically say, oh, what the group is going to look like. But there turns out to be some other ways we can address this. But let's check out K-means issues first. So this notebook, so some obvious issues is that initial parameters matter. So if we don't start off with the right, the right placement of those centers, it might not perform very well. And I think you can probably like kind of think about where that looks like. Like if I were to restart this guy, and I'll go ahead, actually I'm gonna restart and choose Gaussian mixture. And you can imagine if I put, for example, all the points right here, it might take a while for it to actually perform well. But what's even worse is that if I go ahead and choose this, there's a way I can choose this where maybe, for example, this isn't going to, this is me just trying to get it good. Sorry, I'm trying to think this on the fly. But you can imagine putting these centers, like the placement of this actually really matters. And I'll show an example of that in a second. If I try to run it, I think it'll actually figure it out. But that's a big concern. And one is that clusters are not always what we expect. So sometimes you can actually get these weird like clusters that don't actually intuitively make sense, but the algorithm optimized for this. And this is because of this local minimum. It finds something that's a good enough answer, but not the best answer. Okay, so this is where I have a little demonstration of like how to make this work. So we're going to look at, so I found a couple examples where there's clearly obvious groups, but it's not going to, we're going to place the cluster, we're going to purposely try to place the centers so the clusters actually aren't identified well. So if you see this part right here, our 3 little blobs, this seems like relatively like, okay, yeah, we could probably figure this one out. For example, we saw this basically is what this one is right here. But I'm going to challenge you guys. Let's use 3 centers to basically find a local minimum. So not the best answer, but like an answer that the algorithm won't really perform better, where essentially there's going to be one group on the left. So these 2 groups will be considered one group. And we can say like another group on the right. I'll let you know is that basically if you had 3 centroids, this will technically make into 2 groups. But the goal here is like if you can make this into one group. And we've got an idea of where we would place those 3 centers. Yeah, so, and remember, it's going to always try to find like the closest points and just assign them. So this one I'll give you guys because this is our first one. So one thing we could do, well, let's go check out the solution. I'll explain it afterwards. So I make these little points. So if you have it just randomly kind of go through, these are kind of equally spaced along this part, and you have these in between, this is going to be identified as one group, and these 2 will basically fight over these points. But these points are so far away, it's never going to label these. And essentially what's going to happen, this is going to be labeled as one group, and this group is going to be split in half. So we can actually kind of emulate this over here. Let's see if we can get it. And note that this technically will have to be like pretty precise. Oops, I had centroid. Oh, I have to choose. So let's say we add our first centroid right here. So now that's relatively equal between the 2. And we add 2 of them like this. So note basically that these points are kind of closest to it, and they're going to fight over these 2 points. But this red is far enough away that this might actually stay over here. So let's see if this will work. So you can see here, basically, it never goes out of that local minimum, where we know the best place, which essentially, if this green one just came off to a little bit to the side here, or this red one came off to a little bit left, you might actually be able to perform a little bit better. If I were to try to redo this a little bit, note that these kind of like things would have to be, keep doing that. There we go. We can see like if I off a little bit over here, a little right here, a little right here, you can see just by having that one point right there, we'll probably end up getting into the spot that we want. It might take some time. In this case, it actually went back to its spot. So you can see here, even what seems like, you know, like, oh, that would eventually get over there. You can see it can get into a non-obvious clustering, and that's just might be out of pure chance. Okay, makes sense? Okay, so here's another example, and I'll challenge you guys with this. So now we have two obvious groups, and I'm gonna say you can put in two centers, so just two, but there's a way to make this essentially where, sorry, this is phrased wrong. I wrote this wrong, but I'll say that basically you can make two different groups that are not just blue and orange. You can split them up into different groups. And we got a guess of like where you would put those two centers to make the two non-obvious groups.
Maybe you could, oh, go ahead, Lauren.
Well, I was thinking maybe in the middle, like at 0.5 on the x-axis. You could do it at the, like towards the bottom and then towards the top.
So one right here.
Yeah.
And one right here. Okay. And then Jenny, was that similar to what you were going to say too?
Yeah, exactly.
Okay, yeah. And that's what I would conclude too, is that if I were to do this, you can kind of see that's kind of like what would happen, right? And that's because essentially everything on the top here would be kind of claimed as its own, and this one over here. And note that this would have to rely on the fact that these groups are more or less parallel, you know, to each other. And we're just kind of like saying, you know, if it started like dipping off to the side, it might kind of catch this part. But you can see that maybe this is an unlikely thing to happen, but it's technically possible. So you always have to be aware. So how could we like fix this? Like, what's one possible solution to like fix this issue where like where we place the centers like really matter?
Well, if there are only two dimensions, we can just look at it. But
yeah.
if there's more than two dimensions,
yeah,
then
right. Yeah, right. So like this is one of those things like, you know, if you could look at it, you know, awesome, right? It can always say, oh, this has made intuitive sense. Also, you know, applying the algorithm and then seeing if those results make sense. One solution too is just essentially it's like, well, it just happened to be like if these were off like a little bit to the left and a little bit to the right, those might help. So having it done over multiple times randomly chosen. The way I kind of put this analogy is like if you remember back like we did gradient descent and we're kind of climbing down the hill. And imagine that's our optimal spot. And we have this little tiny hill right here, right? Is that if we started off to the right here, and we imagine like this kind of ball or someone kind of going down the hill right here, they might find this local minimum here, right? That's where they end up finding this part. But if you started off on this side, well, maybe you end up going right here and you wouldn't find this local minimum. So one thing you can do is basically have random starts, do this multiple times and see where it goes through. But now you can see already, it's like, okay, now we got to do it multiple times to make sure we find this, you know, global minimum. You can see that we're kind of adding more and more to it, but that's one solution we could do. Okay. So.
And Victor, what is the metric that we actually compare when we do it multiple times? Like what number do I look at multiple times to know whether I've got weird clusters?
Right. Basically the average distance.
Okay.
So you can imagine like when we did back like in what's it called? Oops. When we did back when linear regression, when we had a line like this and we had points, we measured how far it were from that line. Same idea here, where basically we take each of these, let's say these centers, and we say how far are they from those points that are assigned to it. That makes sense?
Right. So if the centroids are actually in the centers of clusters, it'll be low. And if the centroids are like out in space somewhere, everybody's average distance is going to be really high.
Right. So like, for example, this brown one will do really well, but if you look at this red, it'll look something like this, where the average distance is going to be relatively large compared to this guy.
Okay. And where, sorry, I feel like I should know this because I went through the lab,
That's
but
right.
where, how do I access that information? I mean, where do
Oh.
I, how do I actually get that out?
Yeah, so if you remember back when we did K-nearest neighbors, we had our different district metrics. So let's say like Euclidean distance.
Okay.
You can do the same thing where essentially you say, if this is multiple dimensions, you just have, multiple distances for each part of that dimension and take the square root or whatever distance metric you would use.
Okay, thank you.
No problem. Yeah, good questions. Right. Yeah, the main thing is basically saying, how far are you from these points? And that's kind of all we have really. Just quick summary is that like K-means relies on distance centers. It looks for blobs of data. It doesn't do very well with things that are not blobs essentially. If you have something like a moon kind of shape or something that's kind of like an elongated shape or, concentric circles, like it has a real hard time trying to figure that out. Okay, and again, I'll point to this guy right here. Okay, so this kind of leads us like, okay, well, K-means like, yeah, it's not bad, but there's some obvious issues. So we can talk about some other clustering algorithms. So the next one we talk about in clustering algorithms from the curriculum is hierarchical clustering. Oh, I guess agglomerative. I can never pronounce it, bro.